All of you understood this? This is the way you can understand the instruction. And this is an example of indirect addressing mode. Okay, see here, indirect data is going from a register, 8-bit register, to the memory, right? So see here, this is your source, this is the destination. This is the source, this is the destination. Okay, so I'm just telling you how the data is getting transferred. Okay, now see here, I have a small animation. Just check how the data is going. See, what is this? Tell me. This is your registers in the memory. Sorry, microprocessor. Okay, this is a microprocessor. Okay, and I told you that as a programmer, you're supposed to know only the which are registers available. And you can see this DS, CS, SS, ES, AX, BX, CX, DX, SP, BP, SI, DI, all these are registers in the microprocessor. This is the internal part of the microprocessor. In the right side, you see is the memory, right? So this instruction, what it does, it will copy the content from the lower or higher order byte of BX register to the memory. Where in memory? In memory, yeah, memory, there's some offset address. See, moment memory comes, there's an offset address, right? Where the offset address is available in the SA register. So it has to pick the offset address and then it has to take the data. Now look at this. Look at this. Now see here, your BX register is having a data 8A17. Can you see here? You can see the light blinking there. Okay, 8A17 is the data in the BX register. Okay, now you can see that your data has to transfer, BH has to transfer from to the memory. Where in memory? When moment you say it's memory, it's a square bracket corresponds to memory, it needs an address, offset address. Where is the offset address? Offset address is available in the SA register. Okay, so where is SA register? See here, SA register. Can you see offset address in SA register? So now offset address to where the data has to be transferred to the memory is available in the SA register. It will pick that. Microprocessor will pick that. Okay, and then it will transfer the data to the memory. See, you can see here. You can see here. Right? Okay. So you can see that 8A is transferred to the memory. Can you see here? Okay, you see. The data segment is, what is the content of data segment? What is there in data segment? 2000, right? It's given. Your data segment register is having 2000. So it will use this content of the data segment, content of SI, content of BX, and then it will perform this instruction. Okay, it will perform this instruction. You can see here. Data segment is 2000H. It will use that and see how the data is transferred. And physically where the data is stored in is the physical address of the memory. Okay, the physical address is 2D600. This is the physical address of the memory. This is the way this particular instruction is getting executed. Right? Okay. So hope all of you understood about this. Now, can we convert this into machine code? Can we convert this into machine code? Shall we convert this into machine code? It's very easy. I will tell you. Just concentrate here and do it along with me. Okay. Now, how do you convert this into the machine code? Very simple. Okay. I told you first, you just have to fill this binary values. You just have to fill this binary values. Now, D50 into D10. First, start from D50 to D10. What is D50 to D10? It is corresponding to the opcode. What is the opcode here? What is the opcode here? Tell me. Opcode is move. You know, for move, what is the combination of opcode? It is 100010. Most of the move instruction will have an opcode of 100010. See, there are so many opcodes, right? Okay, there are so many opcodes. Don't think that you need to remember every opcodes, right? There's so many instructions, right? Your machine, your assembly instructions are so many, you know that, right? But how do you remember this 6-bit combination for each and every opcodes? It's not required. It will be given in a table. Don't worry about it. Okay, just you need to know how to put it in this place, D15 to D10. This is very important for you to know. Okay, fine. So first move. First put that 6-bit combination D15 to D10 for the move instruction. First you do that. Okay, so now that is 1 0 0 0 1 0. Okay, this is fixed now. This is fixed. This is fixed. After that comes your D bit. After that comes your D bit. Can you tell me? Okay, what is D bit here? It is data is coming from the register, right? Okay, so hope all of you remember that when the data is coming from the register, what is D bit? 0, right? Very good, very good. So when the data is coming from the register, why data coming from the register? Can you see? Data is coming from the register. This is the source, the destination. Data is coming from the register. Okay, so data is coming from the register. Now, which register is that? BH register. Okay, now what will be the D bit? D bit is 0, right? D bit is 0. See, moment you fix your D bit, you know which register is that. Same time you can put REG also immediately, right? Now, you know, data is coming from the register. Which register is that? BH register. That is what this REG is. Immediately you refer to the table. You refer to the table. This is the table, right? You refer to the table. See that what is that 3-bit combination? That is D5, D4, D3 for that register. Now, which register is here? Register is BH, right? Okay. So now where is BH register? This is BH register. Now, what code you can fix for this? You can fix the code 1 1 1 here. Immediately after D bit, try to fix this REG. Right? Okay. Sorry, this one, D5. Okay. Then it comes. This is remaining. The memory part is remaining. This memory part can be done by using mode bit and R by N. Okay. Now, for this mode bit and R by M bit, refer to the one more table. Refer to the one more table. Okay. Now, can you find something like this within the square bracket? SI in the table. Can you find that? Where you can find? Can tell me? Within the square bracket, only SI. Can you find it here, right? Yes or no? You can find it here. What is the corresponding mode bit? What is the corresponding R by M bit? Try to find out corresponding mode bit and corresponding R by M bit. You fix it. You fix it here. You fix it here. Mode bit is 0 0 and R by M bit is 1 0 0 1 0 0. Check. Check where exactly mode bit is 0 0. R by M is 1 0 0. Now, what is the final machine instruction? The final machine instruction is 1 0 0 0 1 0 0 0 0 0 1 1 1 1 0 0. I lost a lot of energy. Is it feasible to read every time 16-bit value? So what do? You make it as a hexadecimal value. Now, there is nothing more required as a part of the instruction, right? In direct addressing mode, your offset address is mentioned in the instruction itself. In such cases, you have to put it along the machine instruction, 16-bit instruction. Here, there's nothing, right? Anything as any number as a part of the instruction, you have to put it here. But here, there's nothing, right? So your complete machine instruction is now this one. Your complete machine instruction is now 883C, right? The complete machine instruction is 883C. Okay, this I will take it later. This is the reverse one. It's converting from machine instruction to the assembly instruction. That's also possible. Okay, I will take it in the later stages. But before, hope all of you understood how do you convert your a basic step to convert your assembly instruction to machine instruction? It's very easy, very easy. We'll do some more problems. Let us see. I have some problems already mentioned here. This is the reverse one. I will take it little later. Once you are get acquainted with the.
So in machine, if there's an indirect addressing, we cannot add the bytes that were getting shifted. Like the contents of which we cannot because in direct we directly have the exact value we have to make.
Yeah.
So,
No, I didn't get your question.
So like in the first where there was direct addressing, we did add the low bytes and higher bytes.
But in this it's not there. It's not there because this is not this indirect address, right? Already your offset is available in SA register.
So
need not, because it's not a part of the instruction. I understood your doubts, right? If it is for direct addressing, see if any number is a part of the instruction, then you need to add, you have to add it to the instruction, 16-bit instruction. For example, in direct addressing, we have added lower byte first and higher byte first because it's a part of the instruction. But if you see in this, see, I'll go back to this. I'll go back to this. Now the original. Here, if you see this, there's no number which is a part of the instruction. Can you see this here? If you see this instruction, right, in the direct addressing mode, here you will have 1234H. This 1234H is part of the instruction. You understood this? Okay. So because of that, once you convert this instruction into the machine instruction, you have to append this 3412 this, like you have done earlier. But for this is not required because this instruction is itself is move within the server bracket SI and BH. This doesn't have any number which represents part of the instruction. Have understood this? Okay, in such cases, you need not put that lower byte and higher byte. But if any number is there, you have to put. For direct addressing, you have to put. For immediate addressing, you have to do that. We'll do one problem for the immediate addressing. Okay. Okay. So let us do some problems now. Let us solve some more problems. Hope all of you understood this. I'll go to some examples. See here. See the instruction. What type of addressing mode is this? Can you tell me? What type of addressing mode is this? It is example of, it is direct, it is immediate addressing mode. Why it is immediate addressing mode? Because yes, data is available as immediately after the instruction. In the instruction. Now see here. Now tell me what this instruction does. It will copy a 16-bit content into the AX register, right? Or else we can say it will copy a 16-bit content, immediate content. It will copy a 16-bit immediate content. Can you see this is the 16-bit immediate content into the register AX? See, this is source. This is destination, right? Now source is an immediate data here. It is neither memory nor register. So an immediate data is transferred to the register AX. The addressing mode for this is going to be what? This is called as immediate addressing mode. I have told you about this immediate addressing mode. Don't forget this. Why it is called immediate addressing mode? Because your data is available immediately in the instruction itself. Now, how do we convert this into machine instruction? So this particular addressing format will have little different addressing instruction format. Okay, this is an example of immediate addressing mode. Now, what is the format? Listen carefully here. There's only a register here. You don't have, see, the other type of instruction format, you have a register and you have a memory or register, right? Right? Because of that, you need that mode bit and R by N bit, right? But here you have only register. Always here, data is going to the register. Always, this type of instruction, always your data is going to the register, yes or no? Do you need a D bit for this? Do you need a D bit to separate or decode this instruction? Not required, because this type of instruction, always your D bit is going to be 1, right? 0 going to the register, right? 0. So your instruction format need not have D bit at all, right? Your instruction format need not have D bit at all, right? So why I'm telling you this type of instruction will have slightly different instruction format compared to the one you have already done. I've understood this. Okay, that's why I'm telling you here certain bits are not required. D bit is not required. Why D bit is not required? Because your data is always going to the register. There's no option, another option, right? It's always. That's why D bit is not required in this. Okay, but you require W bit. W bit tells you what of data transfer, whether it is 16 bit or 8 bit. Okay, it's also possible that you have instruction move AL comma 12H. Now tell me, what is that something getting copied to the AL register? 12H. It's a 8-bit data. It's a 16-bit data. This is 8-bit data. Of course, in this case, W bit is going to be 1. Right? Oh, sorry, 0, 0. I'm sorry. Yeah. In this case, W bit is going to be 1. Right? So W bit is required. Right? So data is going always to the register. So because of that, the instruction format, the 16-bit instruction format, that's the machine instruction format, is slightly different here. Right? What is that? First comes opcode. Okay. So for this opcode, the move instruction in immediate addressing mode, when you use move instruction with the immediate addressing mode, the opcode is going to be only 4-bit, not 6-bit, like in the other format. Okay, right? Now, opcode is going to be 1011. 1011. Then you will have a W bit. Okay, what is the W bit here? It is 1 because it's a 16-bit transfer. Okay, now W bit is 1. Okay, because it is 16-bit. Look at this. Okay, W bit is 1. Okay, now you see W bit is 1. Now you see what is REG? Register bit. You know, data is going to the register. Which register? Same table you use. Okay, same table. What is the table? This table. So what is there for your AX register? It is 000. You fix that 000 here. Okay. Now, is it over? No. You know, I told you those numbers are part of instruction. Those numbers you have to embed, put it after the machine instruction. What is that? Lower byte first, upper byte next. Okay. Now, what you get a machine code is equal to B83412. This is going to be a machine code for the assembly code move AX, 1234H. This is the way you convert your assembly instruction to the machine instruction. Okay, it's very easy. I told you that don't lose marks in this. Now, okay, now can you do this? Can you do this yourself? I want you to try. Those who are in online, please try this. What is the opcode? This is the same instruction format. This is not immediate addressing mode. What type of addressing mode is this? Tell me. This is indirect. Register indirect addressing mode. Okay. Now tell me, register indirect addressing mode. Okay. What is going to be your opcode? 1 0 0 0 1 0. Okay, fill it. Opcode is going to be 1 0 0 0 1 0. Can you tell me what is D bit? Data is coming from the register, right? Okay. Now, what is that? If the data is coming from the register, 0. Okay, you should remember it. Okay, this is 0. Immediately try to fill REG. Okay, from the table. Okay. Now, what is W bit? Why W bit is 0?
CL is an 8-bit.
It is a 8-bit transfer. Data transfer is 8-bit. Okay. Now, next, what is REG? CL register, right? Data is coming from the register. Okay. Now you see here. Now you want to write REG and R by M bit. Okay. Let us write the REG. What is REG? CL register, right? So you refer to the table. You refer to the table. Okay. Now referring to the table, your CL register corresponding data is 001. Fix it in 001. Next comes your mode and R by M bit. Okay. Mode and R by M bit. Okay. Now refer to the other table. Refer to the other table. See where you have this SI within the square bracket SI. Okay. So the mode bit is 00 and R by M bit is 100. You fix it here. Done. So your machine instruction is going to be 880C. No displacement. Displacement is not there because there's nothing as a part of the instruction. Have you understood this? So how to convert it into machine instruction? Okay. How it is stored in the memory? Can you see this? How it is stored in the memory? Suppose if you have a data segment and code segment, this 880C is stored here. Can you see here? 880C. Can you see? 880C is stored in the memory. Because I'm using this is the code segment with the offset address. Okay. So this is the code segment address. This is a segment address. And this is the offset address. In this offset address, how this is stored. See, this is the memory. What you see is the memory. This is the way you can look at the look into the memory. Okay.
So also there in direct and immediate, there's only an 8-bit transfer. We just added to 0 byte, right?
Yes.
Or high byte.
Yes. Always that part of the number which is there in the instruction, you need to add to the machine instruction.
Even for 8-bit, it's just 0 byte, no high byte.
For 8-bit is only one bit. No? How it is stored. Okay. Now tell me, listen carefully. This is very important now. See here. Move AX, comma. This is called as segment overriding. I will tell you what is segment overriding. See this example. Move AX, comma, CS colon DI plus 1000H. Try to understand what is this. First, forget about this. Assume that this is not there. Assume that this is not there. Okay. Now, tell me, what type of addressing mode is this?
Direct.
Is it direct? It's not direct addressing.
It's indirect.
It is indirect, but it is base plus relative. It is register relative addressing mode. Yes or no? You have a relative value here. This is an example of base plus relative, or we can say register relative. This is an indirect addressing mode only, because your address, your offset address of the data which is supposed to be transferred to AX register is available as a sum of DA register content of DA register and 1000H. Right? See here, try to understand. This is the source, right? What is source? Source is the memory. Yes or no? Source is the memory. What is destination? Destination is going to be register. So your REG will be filled using this, and this is going to be part of register memory. This is the memory. This is the memory. I understood this. Now data is going from the memory to the register. Yes or no? Right? So 16-bit data is going from memory to registers. Yes or no? Okay. Now see here. When you try to convert this into the machine instruction, see it part by part. Now, what is the opcode? Opcode is move, right? So definitely this will be 1 0 0 1 1 0 0 0 1 0. What is D bit? D bit is data is going to the register. To the register means definitely it is going to be 1. Then what is W bit? It is 16-bit transfer or 8-bit transfer. It is 16-bit transfer. So it is going to be 1. Now you know data is going to the register, AX register, right? Okay. Which register is that? AX register. Can you immediately fill REG? You can do it, right? It is definitely 000, right, for AX register. Always keep this table in front of you. Okay. It will be given in the exam. Don't worry about it. Okay. Now you see here. Now you see here, your data is going from the memory. How it is going? It is going through another addressing format mode, and this addressing mode you have already know. You already know it, right? So I told you what type of addressing mode is this in my previous lecture. In addressing mode, I told you, right? In addressing mode, what type of addressing mode is this? See this. I told you register relative, right? See, this is register relative. See here. What is register relative? Move AX comma 10 within the square bracket BX. This is same as okay. This is same as. See, this is same as I told you. Move AX within square bracket BX plus 10. Some relative value. This is BX register. This register can be anything. I've understood this. Okay. So addressing mode is this is register relative addressing mode. Okay. Now let us go back here. Addressing mode for this is register relative addressing mode. Okay. Now once you're written your mode bit, that is nothing but your mode bit is nothing but your opcode 100 D bit is going to be 1, W bit is going to be 1, REG is going to be 000. Now see the table. See, I told you initially you forget about this. I will talk about this later. Now look at only this instruction. This instruction is example of register relative. Register relative. Okay. So your REG will be taken care here. Now R by M, okay, which is the memory, you have to put it now. You have to put mode bit and R by M bit. Okay. How do you put that mode bit and R by M bit? I will tell you that. Don't worry. Okay. Now first we will fix the remaining one. Opcode. Okay. D bit 1, direction to the register. W bit is going to be 1. Then REG is definitely is going to, because it's the AX register, it is going to be 000. Now what is mode bit and R by M bit? Look at the table. Look at the table. Look at the table. It is actually DI plus D16. This is 16-bit value, right? You refer to a place where you have DI plus D16. This is your D16. Is the 16-bit value. Try to understand this. This is a 16-bit value, D16 data, 16-bit value. So you need to refer in this table where you have DI plus D16. Where you have DI plus D16? Can you see? In this particular place, you have DI plus D16. Right? Now, see the corresponding mode bit. Corresponding mode bit. What is the corresponding R by M bit? Tell me what is the mode bit and corresponding R by M bit? Mode bit is 10, right? And R by M is 101. 101. Okay, try to fix it. Try to fix it in respect to place. When you fix it in respect to place, you get your complete code. But once again, there's a displacement you have to mention here. Okay, now see here. What is the machine code now? Machine code is 8B85. Is it over? No, you have to fix that relative value along with that. Okay, so after fixing the relative value, how do you fix the relative value? First lower byte, after that higher byte. So now your complete machine instruction is going to be this 8C850010. Okay, the complete machine instruction is 8C850010. This is actually somewhere it is. How to make this, bring it to the side? The way we can bring it to the side. Is it going? No. Anyway, I'll write it here. Don't worry. B, yeah? Yeah. Right. 8B, not 8C. Because 1011, right? 1011 is going to be B. 8B85. Okay. So it is going to be 8B85. Then this displacement. First comes lower byte 00, then comes higher byte 10. This is the machine instruction. This is the machine instruction. Now I will come back to this CS. I will come back to this CS. Listen carefully. This is very important. You need to remember. Now, if this is not there, right? In this case, a data, okay, data is coming from data segment. Okay. By default, if this is not there, data is coming from the data segment by default. But in this case, because you have put this CS colon, you are forcing the data to come from the CS code segment. You are forcing, right? So since you are forcing it and you are actually mentioned it in the instruction, your machine instruction will have a prefix. Your machine instruction will have a prefix. Now, what is that prefix? Okay, what is that prefix? This table will be given to you. This corresponding table will be given to you. Now, here, can you see you are overriding, somewhere you are trying to override the data segment, right? Using code segment, right? Now, somewhere you are overriding the segment register here, mentioning that data is coming from code segment. I told you if this is not there, by default, data is coming from data segment. Since you have put CS colon, data is now you are forcefully getting from the code segment. That's why you are trying to override segment registers. So that information of overriding, you need to put it in the machine instruction. Now, which is that segment register you are overriding? Code segment, right? The corresponding segment override prefix is for the code segment register is 2EH. 2EH. Suppose instead of CS, if I have, for example, SS, what is the prefix? Prefix is going to be 36H, right? Suppose if you have ES, prefix is going to be 26H. That's why what you do, along with this 8B, along with 8B85, see your machine instruction is now, your machine instruction is now 8B85. Of course, the displacement will come 0010. You just have to put this prefix. What's the prefix? prefix corresponding to CS is 2E. You just put it here. That's all. That's all. This you do whenever there is a segment overriding. You can see this is called as segment overriding. We are overriding the segment. Understood this? Okay. So now this is going to be the machine instruction, okay, for the assembly instruction given here. Now almost you know how to convert your assembly instruction to the machine instruction, right? Okay, so I will give some more problems to you. Don't worry, I will give some more problems to you. More practice will make you perfect. So let us go for some more. Okay, this is the way data is stored. Okay, some more examples I will give you. I will just go to the tutorial questions and I will tell you how to do this. I'll go to tutorials now so that we do some more problems. We'll go to tutorials. Let us see what are the questions given there. Okay, so here we have something. Yes. Okay, see, whatever we have now studied, it is actually 16-bit instruction format, and it is for 16-bit mode of operation. Assuming that 16-bit mode of operation. What is that 16-bit mode of operation? We are assuming that our data, right, our instruction, everything is of 16-bit. 16-bit mode of operation means whether it is offset address, whether it is a data, everything is 16-bit. Okay, you understood? Okay, hence it is called as 16-bit mode of operation, right? In 16-bit mode of operation, you will have your offset address to be only 16-bit. Your registers will be only 16-bit, right? Okay, your offset is address is 16-bit, registers are 16-bit. Okay, see, these registers, it need not be always 16-bit. It can be 32-bit also, right? The program which is written for 16-bit microprocessor should execute in 32-bit microprocessor also. Assume that you have written a program when you had only 16-bit microprocessor. Okay, as the day grows, as a year, as technologies advance, 16-bit microprocessor will become obsolete. Only 32-bit will come. In such case, do you need to write the program again? Right? You need not write the program again. Have understood this? So in such cases, we give some prefixes to the program. Okay, if it is to be used for the 32-bit mode of operation, when your register size, your address size, everything is offset address size is becoming 32-bit. right? See, this AX, BX, CX, DX, all these things, whatever you see in microprocessor, it's all used for 16-bit mode of operation. Moment you go 32-bit mode of operation, your register will become EAX, EBX, ECX, and EDX, and so on. Right? These registers are normally, it is given like this. Listen carefully. It's very easy to remember. See here. These are the registers. So hope those who are in online, you are able to see the board, right?
Yes, sir.
Yeah. Just if anything you put in the message. Now see here. This is total is, assume that 32-bit. Okay. In 8086, you have, right? I will put it like this. How the registers are normally, So this is going to be 16-bit, yes or no? This is 16-bit. Out of that, you have 8-bit, 8-bit. These general purpose registers, AX, BX, CX, DX, right? You have SI, you have stack pointer, you have base pointer, right? Now you see, we write this as AX, BX, CX, DX. This same AX can be used as AH and AL separately as a 2 8-bit. This is possible only for the general purpose register, CH, CL. This else can be used DH and DL. But stack pointer has to be used for 8086 microprocessor. The stack pointer has to be used fully 16-bit. You cannot divide it. Stack pointer, base pointer, source index, and destination index, everything has to be used 16-bit. Now, suppose if your microprocessor is 32-bit, right? The same name, okay, will be called as the registers are called as AX register is called as EAX, BX register called as EBX, CX register is called as ECX, DX register is called as EDX. Fine. Okay. So this is called extended registers, which is actually 32-bit. Whenever you do 32-bit mode of operation, right? Doing 32-bit mode of operation means using 32-bit registers, right? So when you use 16-bit microprocessor for 32-bit mode of operation, you can do that, right? You can do that. Whenever you use your 16-bit microprocessor, which is 8086, for 32-bit mode of operation, it will have 32-bit register in it, and that it may have 32-bit offset address in it. In such cases, you have to mention in the assembly instruction or machine instruction that you are using 16-bit mode of operation, but using 32-bit registers by using some prefixes. I will tell you that. Suppose you are using 32-bit mode of operation, okay, and then you are having 16-bit registers in that, then once again there is something called violation, right? That in such cases also you have to tell the microprocessor by giving some prefixes. Understood that? Okay, I will tell you that by solving one question. Okay, where to put the prefixes, where not to put the prefixes. Remember this. This is very important. Okay, so now I told you about 32-bit registers. Now here, see the question. See the question here. For the following instruction, determine the addressing mode and the machine code. Assume instructions are in the 16-bit mode of operation. What is the meaning of 16-bit mode of operation? If I say 16-bit mode of operation, that means your instructions should have 16-bit registers and 16-bit offset address. If it is not, right, you can see If it is not, you have EAX here, 32 bit. This is 32 bit. There's a violation. It's called violation. You are trying to do only 16 bit mode operation, but in this case, what you have 32 bit register is a violation. 9 Safi, right? Such cases has to be dealt, and what you're going to do is just put one prefix. There is something called, this is the register violation, register size violation. Similarly, you can have, see, for example, can you see here? Can you see here? You are using 16-bit mode of operation, but you have 32-bit register and 32-bit value, right? This is called as data size violation. Data size violation. I've understood this. Okay. Suppose now, if you have 40200, is it not that you are adding a number which is more than 16 bit? Yes or no? Suppose if you have 40200100, suppose this is the number. So you have register size of the violation because you are assuming it has a 16-bit mode of operation, but your instruction has got 32-bit register and also 32-bit relative value violation. I've understood this. Okay, so this is called as violation, and this violation has to be dealt properly. Now, how to do that? Okay, we'll see that. How to solve this? We'll see this. Okay, it's very easy. I'll tell you. Okay, now, can you do this now? Move AX, BX plus 1000H. I think I have a couple of solved the problem. Okay, anyway, I'll do it. I'll do it on the board. Don't worry. I'll do it on the board. Okay, move AX, BX plus 100H. Okay, it's very easy. What is the question? Question is move AX, BX plus 1000H. You have to convert this into machine instruction. Okay, first opcode. What is the opcode? Opcode is move 10010. Next is D bit, right? Next is D bit. Okay, next is D bit. Next is D bit. What is D bit? D bit is going to be 1. Why D bit is going to be 1? Data is going to the register. Okay. Now tell me, what is W bit? Your W bit is going to be 1. Okay, then immediately try to fill REG. What is REG bit now? It is AX, right? Refer to the table. Table is 0, 0, 0. Right? So what is required is now mod bit and R by M bit. Okay. Now, for that, can you refer to the table? I think I have to come out of the screen if I want to do that. Okay, let me check. I can show you. Yes. Now, what is that something which is required? Tell me. BX plus 100, right? Where is the table? Table is here.
BX plus D16.
So where is? Hello? Yeah, tell me.
Sir, we refer to the table, it will be BX plus D16, right?
Exactly. So where is BX plus D16 here? Yeah, see here. BX plus D16, yes or no? Here, yes or no? Right? So what is the corresponding mod bit? 10. What is corresponding R by M? 1111. Okay, so I'll go back to my screen. Mod bit is 10. This is 0, 0, 0 anyway. And what is R by M bit? 1, 1, 1. Now, what is the assembly code now? Sorry, machine code now? Make a group of 4, 4, na? Right? Yeah. This displacement also you have to have. What is this? This is going to be 8. This is 1011. How much? B, right? B, and then 8, 7. Then lower byte of this. Lower byte of this is going to be 0, 0. Upper byte of this is going to be 1, 0. So your machine instruction is, this is going to be your machine instruction. So this is the machine instruction for, okay. Machine instruction. This is what stored in the memory. Just have to remember this. Even today, you write a program in Python or write the program in any language. Ultimately, when it is stored in the memory, right, from where microprocessor will fetch is this one only. Because your microprocessor can understand only machine language. It cannot understand all hi-fi Python. It is for you to write the program. That's all. Right? But you need not do the conversion by writing this. Right? Compiler will do. That's why compiler is actually designed. What is the duty of a compiler? Duty of a compiler is to convert this assembler will do that. Right? Duty of an assembler is to assemble assembly instruction to the machine instruction. But how does your higher language will be converted to machine instruction? Compiler. C compiler. Right? You have Turbo C, Borland C, right? The TASM, which is using is the assembler. Similarly, Python compiler. For everything, compilers are there to convert your higher level language to the assembly. Right? From assembly, you have assembler to convert it into the machine instruction. I've understood this. This is the way your execution of your program happens in the microprocessor. Okay. So now let us see one more question. What's the answer for this? What's the answer for this? It is 8B870010. Okay. Now can you do the second one? Can you do the second one? Just now I did something similar to that. What is that? I did this. Move AX, ES DI plus 1000H. Can you do this? Move AX, you have move AX, you have segment override here. What is the question? Can you write the question? Tell me the question.
Yes.
Huh.
DI plus 100.
Move DI plus 1000H, right? So what you have here is DI plus 1000H. Initially, assume this is not there. This you just fix it as a prefix. Now, can you convert this into your assembly? Sorry, machine. Yeah. First opcode. What is the opcode? 100010. What is D bit? What is W bit? What is REG bit? Now, what is mode bit and R by M bit? Now, can you refer to that table? I will give. Always try to have the table with you, right? Okay. Always try to have this table with you. Go to the table. DI plus D16, right? What is the? Yeah. See here, DI plus D16. This one, right? Sorry. This one. Okay, what is the mode bit is 10 and 10 and 101, right? So let us go here, 10 and 110, right? Okay, now tell me what is the final machine code? What is the final machine code? You have this 8B 8 5 0 0 1 0 H hexadecimal. This is going to be your machine code. Is it over? You have this segment overriding, right? Now let us go back to the table. Segment overriding. Okay, so where is segment overriding here? You have that, I told you, right? Segment overriding table, where is that?
After this.
Oh, it was in some other this thing, right? Assembly to machine is here. It was here. Ah, here it is. So which is the one overridden here? ES, right? ES. Okay. So I will give you a table for all this. Don't worry. What is that for ES? 26. So you just put 26 8B. So your final machine instruction is 26 8B. No, did you check it? No, E. Maybe H there is written as hexadecimal values. 26. 26. H is hexadecimal. It's not a number, it's just a representation. Okay. So 268B 850010. This is going to be your machine instruction. This is going to be your machine instruction. Right? Let us do one more question. So would you like to have 5 minutes break? Relax. Right? Okay, you do the problem. We'll do the problem. No problem. So maybe monotonous lecture, you may feel a little bored, but let us do the problems. Okay, so how many questions we did now? We did 2 questions, right? This is done. This is done. Right? This is done. Hope you got this answer. Now, let us do this. Let us do this. Here there is a violation. And how to deal with that violation, we will see. Okay? How to do that with that violation, we will see. Okay? Now, let us take that question. Move EAX. Can you take down the question? Move EAX, comma 4020 BX plus DI plus. Can you tell me what type of addressing mode is this? Register relative. What type of addressing mode is this? Register relative. This one, register plus index plus relative. Register plus index plus relative. See, right? Okay. Can you take down this question? The question is, move EAX. See, here you have 32-bit register, but you are using 16-bit mode of operation. There is a violation. How to deal with that violation, I will tell you. Okay. Now, here 4020 BX plus DI plus something is there? Nothing is there. Okay, nothing is there. See, just listen. This instruction is similar to. Okay. This is almost same to. Almost no, not same, not almost. Move EAX. Okay. BX plus DI plus 4020. See, can you see this? This is a offset address, right? This is going to be offset address. What this instruction does? This copies content of memory to the 32-bit register. Can you see here? I understood that, but it is doing in 16-bit mode of operation. Right, then we have to mention about the violation, that's all. While converting, you do whatever you do for 16-bit mode of operation. Right, but before the machine instruction, you put a prefix to say that there is a register size violation. See here, for 16-bit mode of operation, listen carefully, for 16-bit mode of operation, there is violation here. Yes or no? When you say 16-bit mode of operation and you try to put 32-bit register, there is a violation. Suppose if I say 32-bit mode of operation, there is no violation. But if you look at this offset address, which is 16-bit, and there is an address violation, offset address violation, right? So now for 16-bit mode operation, there is a register size violation, no address size violation. So in this instruction, address size is 16-bit only. This is 16-bit, right? This is 16-bit. This is 16-bit. Okay, no problem, no violation. Right? For 16-bit mode of operation, listen carefully, don't get confused. There is a violation. What is the violation? Register size violation. Now offset address. Offset address is 16-bit only. And you're assuming it to be 16-bit operation, no violation. You understood now? For example, if you assume 32-bit mode of operation, there is no violation here. But there is a violation here. You are telling 32-bit and you are using 16-bit address. There is a violation. Yes or no? Right? That's why a prefix. See, while converting, you convert as it is. But these violation prefixes are put before the machine code. You understood this? Okay. So there is some 66 for register size, 76 for some offset address violation. Some code is there. Okay. That code you have to fix. Don't worry. Right? Okay. 66 and 67. Okay. I will tell you that. Don't worry. Okay. So have you understood about these violations? Okay. Now these things are pakka while doing problems. Right? Okay. Now can you convert this into machine code? It's very easy. I'll tell you. This is an example for base register relative addressing mode. Right? Okay. And let us convert this into your machine instruction. Okay. First, opcode. What is opcode? 1 0 0 0 1 0. Okay, what is D bit? D bit is going to be 1. Now, what is W bit? also 1. 16 bit more than 16 also it is 1. Okay, so you make it 1. Okay, what is your REG now? EAX. Refer to the table. 0, 0, 0. Yes, refer to the table. 0, 0, 0. Now you have to refer to the another table, okay, where you have something like BX plus DI plus D16. Okay, let us go to the table now. Let us go to the table. Okay, now can you tell me where is that BX plus DI, right? Yes, 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 yes. Now tell me what is your, see this one, right? This is the one you're supposed to refer, right? Mode bit is 10 and R by M bit is 001. So 10001. 10001. 10001. Right? Now tell me, what is the machine code? Final machine code. I will tell you what prefix you have to put for violation. Yeah, come on, tell me. You make a group 4 bit. Make a group of 4 bits. It is 8 P 8 1. Is it over? No, you put lower byte 2040. It is not over. You have to put the violation prefix. Here, there's a violation of only register size violation. Okay, so register size violation, the prefix you have to put is this one. Register size violation, the prefix. Yeah, I will just check somewhere. I have one question. Here it is. Okay, see, here there is a register violation, right? EAX. The prefix for register violation is 66. The prefix for register violation is 66. So what you have to put for this now in the front? 66. This 66 is for the violation, register size violation, because we are using 16-bit mode of operation. We already told here you have to use 16-bit mode of operation. Now suppose if I say 32-bit mode of operation, the prefix is not 66, it is 67. Because of the address violation. That's all. Suppose if I say instead of 16-bit, if I say it is 32-bit mode of operation, it is actually that violation you have to take care. That's all. Refer to the question. Answer is C. Answer is here. Same thing. See, same answer, na? 66. Now, can you do the this one? This is an example of immediate addressing mode, right? And can you see here there is a both violation, register size and data size. Both 66 and 67 will come. Can you see here? 66 also will come. 67 also is there. Okay, but anyway, no problem. But definitely there is a register violation. Of course, address violation. There's no address in this, right? That's why 67 has not come here, right? This is the immediate addressing mode. Data is directly coming, right? That's why there is no 67 is not required. Only 66 is required because of the register here. Okay, so can you convert this? Do it yourself. Do it yourself. I told you, right? I just now I did one problem. How to convert this immediate addressing mode into the machine code. Okay, it's very easy. Now you have to tell me now. Tell me that. Okay. Okay. Now tell me what is the opcode for this? I'm doing this. It is not 100010. This is immediate addressing mode. I did one problem. Just tell me. It is 1011, right? 1011. This doesn't have D bit, you know, right? Doesn't have D bit. Okay. Now it is 1011. Okay. Then W bit is there, right? This is 1, right? W bit is 1 because 16-bit mode of operation. Then REG. What is REG? Refer to the table. Refer to the table. Where is the register? Where is the register table? ECX 001. It is 001. 001. Okay. So can you get the hexadecimal equivalent of this? 1011. How much? B, right? Yes or no? B, right? B. 9. Okay. Now you see. Now you see. You have to put this displacement. Now, lowest bit will come first. What is that? 67 will come first. After that, next 12. After that, 00. After that, CC. See, this is the assembly instruction. See the same answer here. Right? Can you do the last one? Ah, yes. Very good. There's a violation, ECS. Register size violation. 66, you have to fix. You have to fix 66 here. Done.
Sir, why did 67 end between the core not in the
Where 67?
So
It's a part
60.
of the, it's a part of the data.
Okay.
Yeah, it is the part of data, right? It's part of data. Yeah.
Data size dimension.
Yeah.
It's not required. So see, we have only offset address size violation and register size violation. Right? Now, since we have already said that there's a register size violation, and your microprocessor will be ready, okay, to accommodate 32-bit data. That's why this is not address, this is the data. If it is address, you have to, it will come under address violation. Sure, definitely, 100%. Right? Okay. I can give an example, for example, like this. I can give an example. Suppose you have an instruction, okay, ECX within the square bracket. I will write 32-bit address. Okay. I will write 32-bit address as 1, 2, 3, 4, 5, 6, 7, 8 H. Right? Assume 16-bit addressing mode. Assume 16-bit addressing mode. When you say assume 16-bit mode of operation, or you can say simply 16-bit mode of operation. You can say 16-bit mode of operation. 16-bit mode of operation. Of course, there's a violation, right? There is a violation of register size. There's a violation of address, offset address size. Right? Now, can you convert this into machine instruction? Quick. You can do that. It's very easy. What is the opcode? 100010. Okay, can you do it? What is the D bit? And this is the example of direct addressing mode, right? Yes. What is D bit? 1. W bit is 1. What is REG? 001. Okay. Now, what is that R by M bit? Actually, you should refer to D16 only, right? We are putting violation anyway, right? You put D16, or you check if any D32 is available there. Just can you check the table? Not available, right? It's not there. You only have D16. Okay, you put that. It is 00110. It is 00110. Okay, now tell me, what is the machine instruction? Come on, 8B0. What is this? E, right? Yes or no? E, 8B0E. Then you have to put this offset displacement 78, 56, 34, and 12. Now, which are the prefixes you have to put? 66 for register size violation, 67 for offset address size violation. So your complete machine instruction is going to be this one. For what type of operation? 16-bit mode of operation. For 16-bit mode of operation. These type of questions you cannot by heart. Okay, so please don't by heart this. Try to know, try to understand, and do it yourself. If you have any problem, you can just contact me for any doubts. Fine. This is the way you have to tackle. Okay. Can you do this? Add AX comma SI. It's very easy. Question is add AX comma SI. Okay. What type of addressing mode is this? Indirect addressing mode, right? Okay. The one operand is available in the register. Other operand is available in the memory. But memory address is not directly mentioned here. But it is available. The offset address is available in the SI register. Offset address is in SI register. Convert this. What you require opcode? What is the opcode? Opcode is add, right? Okay. It is given, right? It is given as 0000. Opcode is Now opcode is 00000. How many zeros? 6 zeros, right? Yeah, 6 zeros. 6 zeros. Okay. Now what is D bit? Data is going to the register 1. What is W bit? 1. Right? What is REG bit? 000. Right? Okay. Now what is mod and R by M? Refer to the table where you have SI. What is that? Table you should always you should have it with you, okay? Because without that you can't do anything. So it is SI, it is 00100, right? 00100. Where is this? We'll close this, okay? Let's see from here. Okay, it is 00100, right? Yes or no? Okay, now is there a displacement? No, right? Can you tell me what is the machine instruction? 0, 3, 0, 4. That's all. That's all. Right? 0304. This is register indirect addressing mode. Okay. So now what we learned is converting from assembly instruction to the machine instruction. Can the reverse possible? Yes, we can do it very easy. Same table you use. I will tell you how to convert from here it is. Okay, now okay, see here. What is given to you is 8B4734. So what will be normally given to you is 8B4734, assuming to be 16-bit instruction format. So if you see this, in this your 16-bit, out of this, okay, see this is 8B47. This is not only 16, you have more than that in this, right? But if you take the first 15, this is going to be your instruction format, right? So what you do first expand that, right? Reverse, you do reverse. When you expand, what you get? 10000. This is 1000. B is 1011. See, when you expand this, you get 1000, 10011. This is 0100, 0111. Now you know the instruction format. Okay. See, you refer to instruction format. I'll repeat again. See, this is your 16-bit instruction. First, convert it into binary. You know, 81000, B1011, 40100, 70111. This is your 16-bit instruction, which you did now in the other way. Okay. Now, you know, the first 6-bit is going to be opcode, right? Now, what is the opcode here? Opcode is 100010. Now, tell me, you know, what is the opcode? Opcode is going to be move. Right? Now, refer to the D bit. What is D bit? D bit is 1, right? That means data is going to the register, right? Okay, going to the register. That means where it will be? It will be in the destination. This is your destination. This is your source, right? That means data is going to the register. That means here you will have only register, right? Okay. Now what is the register? You refer to the REG. Refer to REG. What is that REG? 000. Go to the table. Check. Right? Okay. Now before that, check is there a violation prefix here? Nothing is there. So it is going to be AX, comma. Right? Okay, why it is AX? Why it is not AL? Because of the W bit. Because of the W bit. Okay. Now can you just go to the table and check what is there in your mode 01 and R by M 111? Refer to the table. See. Okay. I will just write again. See, first is your opcode. D bit is 1, data going to the register. Okay. W is 1, 16-bit register. Okay. Refer to the table. Refer to the table. It is definitely going to be 0 AX register. You put AX register there. Now fix the AX register here. Then refer to the mode bit and R by M bit. Which table? Mode bit is 01. R by M bit is 111. Refer to the table. Okay. So which is that place? DX plus D8. DX plus D. Sorry, BX plus D8. Now see here. The displacement is there. What is the displacement? The displacement is this 8-bit displacement 3-4. Okay. So now you see here it is BX plus 3-4. You understood this? Okay. So this is actually converting your machine instruction to the assembly instruction. Okay. This is the way you can convert. Okay. Now see, this is your corresponding assembly instruction for the this one. Okay. See, understood this? Now, can you convert this? Can you do this? 8B00. Can you do this? 8B00. I want you to do this. All of you, do it yourself. Those who are in online, can you do it yourself? Done? Okay. What is the instruction? Opcode is move. Data is going to the register. W is 1. That means 000. Definitely it's going to be AX register. Then you check R by M. Okay. 00000. What is that? 00000?
Yes.
Just check. It is BX plus yes. Yes or no? Right? This is the instruction. Right? Okay. So this is the way you can convert it back to the this one. I have already told you about 32-bit register to you now. Okay. So move EAX comma 1234H. Now you see here your address is offset address is 16-bit, right? Okay. So it is actually transferring the data from a memory. It is transferring 32-bit data from the memory location offset address 1234. So how many locations it is going to read? 4 locations, and it will put the value in the EAX 32-bit register. Okay. So now see here. Refer to this. See here. Assume your DS is equal to 2000H. Offset address is 1234. Right? Okay. So what is the physical address? What is the physical address? It is 21234H. Right? Starting from here, it will read 4 memory location. This is going to be lowest byte, next lowest byte, next lowest byte, next highest byte, next highest, next highest, next highest. Understood this, right? So what it will do, it will read this 32-bit value into the register EAX, right? So when it is reading the value, okay, in the offset address 1234H, you have 74 82, next 82, A3 and 4, 5. This 32-bit value will be read while reading. The first location will have a lowest byte, then next highest byte, next highest byte, and next highest byte. This you have to remember always, because it is reading 32-bit value from a memory location and putting it into. Okay, so when you use 16-bit mode of operation, there's a violation. When you convert this into assembly code for 16-bit mode of operation, there's a violation. Yes or no? That prefix you have to put it. That's all. Nothing else in this. Okay. So let us see that. Opcode 100010. D bit is 1, right? And then W bit is 1, right? What is REG bit? 000. And now this is direct addressing, right? It is 11101. Now see here. Okay. Mode bit is 0. R by M is 101. Okay. So 8B05. Is it over? No. You have to put that 34212 in this. Yes or no? This one you have to put, right? This one you have to put here, right?
So D6.
Yeah.
So in the table for D16, R by M is 110.
110. Okay. So now see, this may be 32-bit mode of operation. So 32-bit mode of operation, you have different table. I will tell you that different table for 32-bit mode of operation. Can you check here?
Oh, yes, it's 101.
Right. Okay. So for 32-bit mode of, this is assuming to be 32-bit mode of operation. Okay. Right. So now if you see here, accordingly it will change. Okay. Accordingly it will change. Be careful about it. Okay. Now see, I will come back here. I'll come back here. Okay. Here, see here. If it is 16-bit mode of operation, okay, you use 16-bit mode table. Okay. Now accordingly you will have a violation because 32-bit is there. Suppose if you have been asked 32-bit mode of operation, okay, for R by M, for modern R by M, use 32-bit table accordingly. Okay. In such cases, that violation will not come. In such case, violation will not come. Okay. So I will see. In such case, violation will not come. Okay. Accordingly, you do it. See, now this is another example. See, another example. This is the example of register indirect addressing mode, right? Okay. Can you write the machine code for this? 100010. D bit is 1, W bit is 1, REG is 00, mode bit is 0000111. You refer to the table. Refer to the table where within the bracket BX is there. Okay. See, within the bracket BX. If it is 32-bit mode of operation, then you would refer to this table. Sorry, 32-bit mode. The table. See here. Where is inside BX? Inside bracket BX. Here. Okay, this is for 32-bit mode of operation. You don't have any 32-bit register in this, right? So you would refer to that table only, because you would refer to this table only. See, this BX. Which table you would refer? This table you would refer. Where is that? Within the bracket BX 1111, right? 11111. You put that. You get this thing. 8B05 66. Why 66 there? We are assuming 16-bit mode of operation, but there is a violation of register size BX. That's why you're putting 66 here. Yes, 16-bit mode of operation violation. That's okay. Now you see here 8B05. Why put 67? Because it's not 21-bit, it's a 30-bit mode of operation. There's a mistake in this. I will correct it. Address size violation, because address size violation is there, right? BX. Okay. So there is one more addressing mode called as scaled index addressing mode. Okay, this is the last addressing mode. I told you that I will do it at the last. Okay. So okay, so it's now 11 o'clock. You want to stop here, or I can continue for some time, and I can complete this scaled indexing addressing mode. Right? Students who are there, let me know you want to continue for some time. So would you like to continue or shall I stop here? Okay, we'll do some problems after 5 minutes. Is it okay? Tutorial problems.
Okay, sir.
Right? We have some tutorial problems. Then we'll stop. Okay? That reverse one. Reverse one. Can you see the reverse one? We'll do reverse one here. See? We'll do this. Okay? Okay. See this. 67, 66, 8B, 86, 0210. See here. Refer to this. See, you have to now look into this before tackling this problem. See here. Listen carefully. It's very important. See here. What is 67? First, you look at the prefixes always. You have a prefix table with you, right? You see any prefixes are there. Now, 67 means there is a address size violation. So in the instruction, if at all any address is there, it is 32-bit address because it is set 16-bit mode of operation. The mode of operation is 16-bit mode of operation. Because 67 is there here means in the instruction there is an address which is 32-bit. First point. Okay. Now 66. That means there is a register violation. Right? Okay. Then definitely this is going to be your 16-bit instruction. 8B86 is going to be your 16-bit. Understood this? Okay. Now you see here, see the things here. Okay. Now you have 8B. Do it. Now what is 8 in the binary? 1000, right? What is B? 1011. What is 8? 1000. What is 6? 0110. Now take first 6 bits. Take first 6 bits. What is that first 6 bits? Opcode, right? Opcode. This is going to be your opcode. What is the opcode? Opcode 1001 means it is move. What is D bit? D bit is 1. Data is going to the register, right? Going to the destination, right? Okay. Now you see clearly. Okay. In this, data is going to the register. This D bit. Now, which is register bit? Which is register bit? This is the register bit, right? Right. Now see here. Be careful. Violation is there. That means the 16-bit mode operation, 32-bit content will come here, right? So which is the register now? EAX. Exactly. Very good. Very good. Very good. EAX. Data is going to the register. Which register? EAX. Why it is EAX? Because you have a register size violation. Now R by M. R by M. Okay. What is the mode bit here? 10. See here. Your mode bit is 10, right? And okay, and R by M bit is 110. Now see here, there's a violation. There's a violation, right? Now tell me which table you have to see here now. You have to put 32-bit wala table where that violation 1 is there, right? Now tell me that for the mode 10, for 110, what is there? Definitely it should be ESI. Can you check? Table. Yes. Sorry, next time I will give the table, okay? Don't worry. Next time I will give the table. 32-bit table. What is 32-bit table? Here. Where is that mode 00? What is the mode?
10.
10. Mode 10 and 110. It is ESI plus D32, right? ESI plus D32. Okay. So what you are going to get here is ESI plus D32. So here you get ESI plus D32, and that D32 is nothing but this one. That 10. What is that? Last you have 1002. It is 1002. See, this is the answer. Can you see? Now, can you do the next one? 268904. Now, see, there's a violation. There is a overriding, right? There's a overriding. 26890. 26.8. What is that? Sorry. 268904. 268904. Now, what is the actually? See the table. It is actually for segment overriding. Yes or no? Segment overriding is a prefix for segment overriding. Okay, let me know. Segment overriding. What is segment overriding?
Yes, it's for years.
ES, right? Segment overriding for ES. Okay. Now, so this is segment overriding for ES. Segment overriding for ES. So wherever memory transfer is there, you have to put ES dot, ES colon, ES colon. Okay. Now, can you convert this into the assembly? 8. 8 means 1 0 0 0 1 0 0 1 0 0 0 0 0 1 0 0. Okay. Now, opcode. What is the opcode? Opcode is definitely going to be move. Okay. And then D bit is 0. What is the meaning of D bit 0? Data coming from the register. Okay. Which register is that? It is 0 0 0. It is AX register. Your source is the register, right? Okay. Now, can you tell me what is W bit? W bit is 1. That's why AX we have put there. Okay. Then what is there something you get it for mode bit mode 0 0? Okay. And R by M is going to be 1 0 0. Tell me. Let us go to the table. You have to refer to the 16-bit table. Now tell me, what is that? What is there in mode bit 0 0 1 0 0? Mode bit 0 0 1 0 0. Yes, I. Yes, I. Now, definitely, this is going to be the SI. Is it over now?
Yeah.
No. You have to put here ES colon. You have to put here ES colon. Why this ES colon? Because you have this segment overriding. That's why you have to put ES colon. This is going to be your final assembly instruction. Assembly instruction for this machine instruction. This is very, very, very important from examination point of view for everything. This conversion from assembly to machine, machine to assembly is very important by taking care of those segment overriding and prefixes, violations. Okay, right? You have to be very careful. See, if it is 16-bit mode of operation, if the instruction has 32-bit register, 30-bit offset address, there's a violation. You have to put the prefixes. Okay, if it is asked 32-bit mode of operation, if there is 16-bit registers there in the instruction, once again there is a violation. Accordingly, you have to put the prefixes. Okay. So sometimes your instruction machine language conversion is correct, but if you put a wrong prefixes, you lose the marks. Be very careful. Okay, this is very important. Okay, so I think we'll stop today. You might have 3 hours will be too much, right? So just try to do some more questions. We have done this almost every questions in this tutorial. Okay, so if at all any no questions is pending in this tutorial, okay, I think we are done. This is the one we did. This is very easy. It's very easy. See, it's very easy. Suppose that in 8086 DS is 1300, content of DS register is 1300, base pointer is 0100, stack segment is register content is 1000, source index register is 0250. Okay, now determine the address accessed by the each of the following instruction. Okay, now see what exactly is this? What exactly is this? Very simple, very simple. I'll tell you, very simple. First, try to understand this this operation. See here, what this does, tell me. This copies data from the memory to the register. Okay, from which offset address it copies the memory. It copies from the memory. The offset address is available in BP plus 200H. Right. So which is the offset address now? That is what actually asked in the question. It is asking how the data is accessed from the memory. So you're supposed to give the offset, physical offset address. Now see, it is coming from base pointer. Right. So now see here, base pointer is a default offset register for stack segment, right? So which one you have to tell me whether data is coming from data segment or stack segment here. Data is coming from stack segment, right? Because of the base pointer. Understood. So now, so your stack segment is 1000, right? Now to get the physical address, shift the segment address by 4-bit position left, you get 1000H. Add the offset. What is the offset? Offset is BP plus 200. What is there in BP? Where is BP? So it is 0100 plus this shift 2000. What is the physical address? 00301. See, this is the answer. Now, can you find out for this? Subtract. That's all. Now it is SI. SI. Now SI is actually default offset register for data segment. Right. So now this will be 13000H. Okay. Now SI. What is SI? SI is 0250. Then it is minus is there, right? Minus 0100. You subtract. That's all. You add, then subtract. That is going to be 13150. That's all. The question asks how the data is accessed, from which address data is accessed. That's all. Right? So now all of you try to practice this, try to practice previous year question papers, and also refer to the slides which I have shared with you. I have not used those slides, but I have used my own way that will convey everything to you, whatever is required, whatever is given in those slides. Okay. So if any doubts, anything, please feel free, okay, to come and meet me. I think in the class, I will do this scaled index addressing mode. In the class, I will do the scaled index addressing mode. Okay. Okay. So there's one more compensatory class I have to take. I will take it in the next Saturday. Okay. So that whatever is syllabus required for your midsem and your quiz, it will be completed by that time. Okay. Right. Whatever we are lagging with respect to other classes, we will be able to complete it. Okay. Syllabus for quiz is this till addressing mode. Till addressing mode. See, this is these slides which we are given you. This till here. 1, 2, 3. Class 1, class 2, class 3. This is what actually addressing modes are. I think whatever is there here, I taught you. Right? It's the same thing, right? Same thing, addressing mode. Whatever is there in the slide, I have taught you this. See, scaled index, I will take it in the class. Okay. Same thing. Whatever is this one. Then I will take flag register also. Okay. There are some possible questions and all are there. Please refer to that. See, these are the, I told you, write a machine code for given instruction using REG and RMIM table. These are the questions which may be asked. Okay, based on the given machine code, you need to answer what type of addressing mode is that. Okay, you should know when to include addressing overrides. All these things, these are the possible questions which you need to. Okay, see here. So this one, the same question, we can do it in two ways. One is for 32-bit mode operation, 16-bit mode of operation. Okay, right? So accordingly, you just have to do the things. Okay. I told you about the overriding, right? 16-bit mode operation, 32-bit addressing mode. Okay, then you have to address violation, you have to put 67. Okay, 32-bit mode operation, 16-bit address, you have to put 67. 67 for address size violation, 66 for register size violation. Just have to see. In the question, it will be given to you, right? That assume 16-bit mode of operation. Assume 32-bit mode of operation. Accordingly, you should put. Okay, fine. Okay, this is almost addressing format is completed except flag registers and the flag registers and the scaled index. Okay, I don't want to continue now. It's already too much to end almost 2 hours. Okay, so I want to stop here now. So in the class, I will complete scaled index addressing mode and the flag registers. Okay, fine. Okay, so if you have any doubts, anything, please feel free to contact me. Don't keep any doubts with you, which is very important. And I will share you some of the old question papers. I think these question papers are available in the library. Solve it. Okay, I'm sure definitely you will be able to do well if you know these very important conversions between assembly to machine to assembly, right? Okay, and also getting the physical address. Okay, but given segment address and offset address. If you know that much, I think you can do well in the quiz, right? So any doubts, anything? Those who are in online, any doubts, anything? Okay, so you can just contact me if there is any doubts. Okay, good. So do well. And also you can refer to my videos. Okay, I have prepared some videos. If at all somebody is still have not come to this session, you can just refer to my videos. Okay, so we'll stop here today. Thank you for coming. So I have only 2 from hostel, remaining people have not come. I expect more people in the class, right? So we will have one more compensatory class for whatever we have not done during last week on next Saturday. Fine. Okay, in the similar way. Okay, okay, then all the best.
Thank you, sir.
Thank you, sir.
Thank you, sir.